Hello and welcome to this Glotaran screencast. Glotaran is an open source and cross-platform application designed to facilitate simple global and target analysis of time-resolved spectroscopy measurements in particular. In this screencast, I will give you a brief demonstration of the workings of Glotaran by analyzing a sample dataset included with the program. The first time you start Glotaran, your window will look something like this. On top of the application window is the menu bar, and directly below that is the toolbar. Using the buttons on the toolbar, one can open an existing project or create a new project, and the same options are also available from the file menu. We will start this demo by creating a new project. Press File and then select New Project. In the New Project wizard that opens, select the Examples category and then the Demo project. Press Next and specify a name, for instance Demo. Then press Finish to create the project. The newly created project directly opens in the Project Explorer and a folder structure for it is automatically generated. Before we can start an analysis, we first need to import the data to analyze. We do this by right-clicking on the Datasets folder and selecting Open Dataset File. We can then open any of the supported data files. A description of each of these files can be found on the Glotaran website under the Documentation link. If the data file is recognized by Glotaran, you can open it by selecting the file and pressing Finish. Note that it is also possible to open multiple files simultaneously by selecting more than one file using Ctrl-click. Once you press Finish, the selected data files will be added as nodes under the Dataset folder. In this case, because we started with the demo project, we already had a dataset available to us, represented by this demo data node. Every data file you open is represented by a data file node in the datasets folder. This is just a shortcut to your data file, if you will, not the actual file. So when we delete a node, it is removed from your project without touching the actual data file, which is what I will do for the two files I added earlier. Now we can open a data file by double-clicking a node or right-clicking and selecting Display Dataset. The dataset will be opened in the Data Editor window in the center of the application. The Data Editor allows us to visualize and inspect the data. In this example, we are looking at a transient absorption spectroscopy measurement. The top left shows a 2D intensity map of the dataset. Here, wavelength is displayed on the horizontal axis and time is displayed on the vertical axis. The amplitude of the data points is represented by the color scaling. Controlling the slides to either side of the intensity map allows us to look at individual traces and spectra in the dataset. Zooming in is possible by clicking in the chart and dragging the mouse from top left to bottom right. Zooming out is possible by clicking and making the reverse motion. Zooming in on a particular region of the data allows us to select a subset of the data for analysis. For instance, we could trim the noisy edges before analysis. Alternatively, one can press the Select button and specify very precisely a specific window. Other basic pre-processing methods are averaging, resampling, baseline subtraction, and outlier correction. Baseline subtraction is probably the most used and most useful method of data pre-processing. It allows one, for instance, to subtract an average spectrum from the data. The default option subtracts the average of a number of spectra at the beginning of the dataset, which can correct for any unrealistic contributions to the data before the moment of excitation. Of course, any form of preprocessing should always be used with caution so as not to induce any artifacts. The most basic form of analysis is available directly from the data editor window. When we select the SVD tab, we are presented with the singular value decomposition of the data matrix. The SVD is a mathematical operation which separates the contribution to the data in linearly independent vectors scaled by number. Here, the left singular vectors represent time traces and the right singular vectors represent spectra. The contribution to the data is the product of the nth left singular vector and right singular vector scaled by the nth singular value. The singular vectors are ordered based on their contribution to the data, as represented by the magnitude of the singular values as shown in a scree plot. SVD analysis allows one to make a rough estimate of the number of rate constants or lifetimes that will be necessary to describe these data in global analysis. By increasing the number of displayed singular vectors, we can see that in this case there seem to be at least 1, 2, 3 linear independent vectors significantly different from the noise, as observed from the presence of significant structure in both singular vectors. The fourth singular vector is clearly lacking structure in the left singular vector. Therefore, 3 rate constants would be a good number to start global analysis with. Note that other than looking at the singular vectors individually, it is possible to use a limited number of singular values in SVD filtering. Again, a data manipulation technique to be used with much caution. Going back to the Data tab. In order to create a dataset for analysis, we first have to select the region we are satisfied with, like so, and then press Create Dataset. We specify a name for this dataset and press OK. Now, a dataset node has appeared under the data file node in the Project Explorer. This is the type of dataset that we can later use for data analysis. In order to start analyzing these data, we first need to create a new analysis scheme. We do this by right-clicking the Analysis Schema folder, selecting New, and then selecting New Analysis Scheme. Or if you do it for the first time, Other, and then in the Glotaran category, selecting New Analysis Scheme. Press Next and specify a file name. Then select Finish. The scheme file is created as a node under the Analysis Schema folder and opens automatically in the editor window. Note the associated palette and properties window with this analysis scheme. This is called the analysis canvas, and there are 3 essential ingredients to be added to this canvas. First, there is the so-called dataset container, which can be created by dragging it from the palette onto the canvas. This dataset container will hold the dataset that we are going to analyze. Second, there is the model container, which represents the model to be used for global or target analysis. This can be created directly from the palette by dragging it onto the canvas, specifying a name, or it can be created by dragging an existing model onto the canvas. Note that any container can again be deleted by right-clicking on the label and selecting Delete Node. Third, there is the so-called output container, which is used to specify where the results should be outputted and how many iterations the optimization algorithm should run for. Again, created by dragging it from the palette onto the canvas. Now before we can do anything else, all of these containers need to be linked to each other by connection arrows. One can do this by holding down the Control key, clicking the label of the container, and then dragging it to another container. The model container needs to be connected to a dataset container, which in turn needs to be connected to an output container. Only then can the analysis be run. If this sounds a bit tricky, that's because it is. A future version of Glotaran will simplify this process. We now have all the ingredients to start an actual analysis. First, we drag the dataset that we created earlier into the dataset container. Second, we need to specify a model. The model is currently empty, but we can drag and drop nodes from the modeling category on the palette onto the model container. The available options are kinetic parameters, instrument response function parameters, dispersion parameters, weighing parameters, and coherent artifact parameters. For advanced user, there is the K-matrix node. This is only necessary when doing target analysis. For global analysis, the kinetic parameters node is sufficient. Once we have dragged a node onto the model, its properties can be changed by selecting the node and going to the properties editor. Before we proceed, we will take a small intermezzo to take another look at our dataset in order to postulate a model that can be used to describe these data. The goal of this intermezzo is to take another look at the dataset and look for clues as to what the underlying model should be. One of the first things that we notice from the 2D intensity map is dispersion. The moment of excitation, or time zero, is dependent on the wavelength. Dispersion can be parameterized in our model. We will get back to this later. But first we look at the most important aspect of our analysis, a correct description of the instrument response function, or IRF. The IRF represents the response of the sample to the initial excitation pulse. Typically this is modeled by a Gaussian function in time with a specific position and width. We can come up with good starting values for these parameters by looking at the data. If we zoom in, we see that the moment of excitation is somewhere around 1 picosecond, and there seems to be a rise of the IRF in about 0.2 picoseconds. For the dispersion, it is necessary to decide on a central wavelength. Here we could choose 530 nanometers, from which point to describe the change in the position of the IRF, which is what the dispersion is. Typically this can be modeled with a second or third order polynomial, so one would need to estimate 2 or 3 reasonable starting values that describe the change in the position of the IRF as a function of wavelength with respect to the central wavelength chosen. I will leave this as an exercise to the viewer, but if you get stuck, simply take a look at the analysis scheme that comes with this demo project. For the final part of this intermezzo, we revisit the SVD of the data, because the next step is to estimate the number of components that we want to attempt to resolve. As we saw earlier in this screencast, SVD is a tool that can help you with this. Earlier we found 3 singular vectors with the contribution to the data significantly different from the noise. For every component that we want to estimate, we need to specify a starting value. Usually the best way to do this is to look at the SVD and estimate the order of the timescale at which the spectral properties change. For this dataset we can see that the processes occur between 1 and 100 picoseconds. So reasonable starting values for the kinetic rate constants would be between 1 and 0.01. Going back to the analysis scheme, we can now start building the model with the parameters that we just investigated. We add the kinetic parameters from the palette and change the number of components to 3. Then we expand the kinpar node and specify some reasonable starting values between the rates that we estimated by looking at the SVD of the data, in this case between 1 and 0.1. In addition to the number of parameters, the kinpar node also allows us to choose if we want to use a sequential model or a parallel model for global analysis. The parallel model is the default, but in this case we will postulate a sequential model. Finally, the kinpar node allows us to restrict the rates that are estimated to be strictly positive, which we will enable. For the IRF parameters, we will use the default Gaussian model, and we will specify the position and width that we estimated earlier. So 1 picosecond for the position and 0.2 picosecond for the width. And finally, we specify the dispersion. The first thing we do is change the central wavelength to the 530 nanometers that we decided on earlier, as it will affect our estimates for the parameters. We will use a third order polynomial to describe the dispersion. This will require us to specify 3 starting values, as the offset is already given by the position of the IRF. Again, we specify some reasonable estimates. Now that the model specification is complete, we save the model by pressing the Save All button from the toolbar. Now we still need to decide what name to give the folder where the results are saved, by giving a name in the output path. For instance, we can call the folder Test. Next, we need to decide what number of iterations to use, and whether we want to calculate the errors for the estimated spectrum, a generally time-consuming process which we'll only do if we have a good enough model. If we leave the number of iterations to 0 for the moment, we can test if our model actually works, or if we made a mistake in the model specification, in which case the analysis will crash. Once the analysis scheme is saved, which we check by looking at the toolbar button, we can now run the analysis by right-clicking the analysis scheme file and selecting Run Analysis. Now, assuming that you have RServe running in the background, the analysis will start as indicated by the progress indicator below. After a few seconds to minutes, depending on the size of the data and the complexity of model, a new folder with results will appear in the result folder. In this case, the folder Test, because we specified Test in the output path. If we expand this folder now, we see the result files. This indicates that the analysis was successful. Because this was only a trial run, and we used only 0 iterations, there's not much point in looking into the results in detail. But what we can do is take a quick look at the main result file to see how good our initial guess of parameters was. We open the file and we are presented with the Overview tab. Here we see the estimated evolution associated spectra, or EAS, the decay associated spectra, and the respective normalized versions. To the right we see the concentration profiles corresponding to the rate constants that we put in the model. As you can see, because we use 0 iterations, they are still the same. At the bottom we see the SVD of the residual matrix with the first and second singular vectors plotted in black and red respectively. Clearly there is still quite some residual structure left, indicating that the model currently doesn't describe the data optimally. But since we haven't iterated and the parameters are still what we initially specified, this is not so surprising. Before we head back to the analysis scheme to let the program iterate a bit, we first take a quick look at the Traces tab. The Traces tab presents us with a detailed view of the quality of the fit. For every time trace and spectra, we can inspect the quality of the fit simply by dragging the sliders. As you can see, it's not even that bad. Apparently our starting values were not too shabby. Overlaid on the 2D intensity map is a dispersion curve in black, which is currently far from optimal, but again not too shabby. Finally, we see again the SVD of the residual matrix. In this case, we can even zoom in and recompute the SVD for a better look. Confident that we are on the right track, let's now go back to the analysis scheme and rerun for a few more iterations. Say 5. After the analysis has completed successfully, you can see that the old results are not overwritten, but instead a new folder is created. This allows for comparison between different analyses run. Now that we have iterated a bit, the first file that we will look at is the summary file. It provides us with a textual summary of the analysis process. Given is the number of iterations, the calls that were made to R in order to perform the analysis, the final residual standard error, and the values of the estimated parameters including their standard errors. If the analysis has failed because the model is wrong or the initial guess of the parameters is too far off, then this file will contain a diagnostic error message rather than the estimated parameters. The next file to look at is the overview file. It contains roughly the same information as the plain text summary file, but it includes a graphical view of the progress of the residual sum of squared errors. The most important thing that this graph tells us is that the fit has converged, as there was little to no progress in the last iteration from 4 to 5. It is an important criteria because before convergence of the fit, we cannot really judge the quality of the model, and it will be hard to tell if the model needs another parameter or whether the program just needs to iterate a bit more. So always check convergence of the fit before you start interpreting the results. Satisfied that our fit has converged, it's time to take a closer look at the main result file with the estimated parameters and spectra. In principle, every dataset will have a result file, so if you analyze multiple datasets simultaneously, you will see multiple files appear. In this case, we have only one. Now the first tab, the Overview tab, shows us the estimated parameters consisting of the 3 estimated rate constants, the 2 estimated IREF parameters, position and width, and the reciprocal of the estimated rate constants, or the lifetimes, and the total RMS error. In addition, we have the evolution associated spectra and the decay associated spectra and their respective normalized versions, and the corresponding concentration profiles in time. Finally, we have the SVD of the residual matrix, showing the 2 first singular vectors in black and red respectively. One of the first things to notice is the reduced structure in the singular vectors, indicating a better fit. However, it is hard to see because most of the data points are located within the first 100 picoseconds, whereas the time axis runs until about 900 picoseconds. One of the things that we can do, of course, is simply to zoom in, or even to open the graph in a new window. But still, the data in the early times can be easily obscured. This is actually a common problem in time-resolved spectroscopy, where one often measures many points in the beginning to capture the ultrafast dynamics and just a few points later on. The problem of visualizing these kind of measurements can be solved by using a linear logarithmic or linlog time axis, which can be enabled by pressing this button. The number controls which part of the chart is linear. In this case, the axis is linear from -1 to 1 picosecond and logarithmic thereafter. The time axis will be centered around time 0, which is defined as the maximum of the IRF. The linlog setting applies to the time traces of the singular value decomposition, the concentration profile, and to the time traces in the traces tab. Especially with the time traces, you can clearly see the improvement by using a linear logarithmic scaling. With the linlog axis enabled, we can more clearly see the remaining residual. Clearly there is some residual on the very short time scale, which spectrally seems a lot like the spectrum at time 0. This could probably be captured by taking into account a so-called coherent artifact, which follows the time profile of the IRF. This, however, is left as an exercise to the viewer. One last tip before concluding this screencast. It is possible to update an existing model with the parameters estimated from the analysis. This can be done by dragging the main result file on top of a model file while holding the Control key, like so. The drop icon will change to include a plus, indicating that the drag and drop operation is indeed possible. You will then be prompted which parameters of the model you would like to update with the estimated values from the analysis file. This little trick should make testing many models less painful and allow you to quickly zoom in on the right model. Of course, when you are finally happy with your model and the quality of the fit, then you still need to make sense of the analysis and try to give a physical interpretation to the results. And that is usually where the real challenge lies. Now with that final remark, I will conclude this screencast. I hope you enjoyed it and are now able to use Glotaran for your own data analysis. If you find any bugs or if you find you are missing certain features, please feel free to contact us and we'll see what we can do.